So welcome. Welcome to Programming with Categories. I'm Brendan. This is David over here. And David and I are researchers here at MIT in the math department, interested in taking this sort of beautiful subject we love called category theory. It's traditionally sort of a more pure mathematical subject, but we're really interested in seeing how it can be applied, how we can do sort of real world work with it, and with these sort of powerful ideas. Bartosz is over here. Bartosz represents the programming side of this course. He's originally a theoretical physicist, but ended up working for Microsoft, and his first book was on C++. But his more recent second book was on sort of category theory for programmers. And so the three of us got talking this summer, and one of the things we talked about was the fact that sort of both programmers, as Bartosz will say more about, are increasingly looking towards category theory, and category theorists are sort of, the two of us are looking towards applications. But there's still sort of a gap between us. We think about the same sorts of things, but with different styles. And so we envisioned creating some sort of a way to sort of close the communication gap, a meeting point between ourselves and our intellectual traditions and our communities. And so we're teaching this course to sort of create this sort of common ground and invite you all to participate in it. So today, we thought it would be worth devoting this class, this hour, to just sort of setting expectations, talking about from our 3 points of view, where we're coming from, and also what you can expect in this space over the next month. So with that in mind, I'm going to hand over to David, who will sort of speak first, and then Bartosz, and then I'll come and close with sort of my point of view and some administrative aspects.
And there are some chairs over there.
Yeah. Thanks for coming, everyone. It's really lovely to see a packed room of excited people.
Yeah, so I'm David. I've been working on applied category theory for about a decade or a little more, basically seeing that there's this mathematics whose job it is to understand models, different models, and how they fit together. Structures, relationships, and, say, organization. So there is a math for that. So that's important in the real world because, like, some people say that all you need to understand the real world is optimization. We're just always optimizing everything. But another point of view is to say that there's structures everywhere and there's relationships everywhere. And neither one is right or wrong, but there are two different kinds of math. And one can be useful for some things and one can be useful for other things. And for building code, for example, for making structured, modular, maintainable code, you do want it to run fast. That is something you care about, so you could go write in assembly. But you also want to be able to work with other people and work on one part while they work on another part and have that all fit together and then change your code a little bit later for some various reasons. And that's kind of how structures fit together. So both of those are important. And since the optimization piece is so prevalent in how people think in engineering, et cetera, we're coming with this other part of math that talks a lot about organization, structures, and how they fit together. So that's kind of why category theory is important in programming. We're going to be building big structures by organizing little pieces. But I also want to give you guys an opportunity to say why you're here. And so one thing we'll be doing throughout the class is instead of a lecture where people don't usually learn as much, we'll be doing a lot of talking at you, but also we want you to be paying, by thinking about stuff and for yourself and having theories about what would be, how these things are working, and et cetera. And anyway, my point is I'd like you to kind of turn to a neighbor and figure out why you're here, ask the other person and tell them why you're here, and then I'll just ask you, just because it helps orient us to what the point is for you guys. So please turn to someone and introduce yourself. Hello, Bartosz. Hi, good to meet you. I'm going to go around. Anything to share from your groups? Any comments that were interesting that you weren't expecting, or any ideas that anyone wants to share? Why is someone here besides me? Yeah, Clement.
I got into category theory because of Bartosz's videos, and I just want to mention that. So this is it's great seeing you guys here organizing this course. But for me, category theory is a language of abstraction, and whenever you start off with a language of abstraction, everything else becomes easier to think about.
Cool, thanks. Yeah, I don't know if the microphone picks that up, but anyway, a language of abstraction. So it's great that Bartosz is here. He's brought category theory to a lot of people, and we really appreciate that. And then as a language of abstraction, that is kind of what category theory is about. I said it was about organizing structures and relationships, but abstraction, somehow those are the same. We'll see if we can clarify that throughout the course. So one reason we're giving the course, first of all, is that Haskell, I'm just learning it for the first time. Bartosz taught me, and it was fantastic, and I really love that language. I learned BASIC when I was a kid, and Pascal and Scheme and stuff like that, and never any, but Haskell is just a really beautiful language in the sense that, and if you don't know any of it, we'll teach you to install it today and get it running. But basically, you can almost read what you write. It's like, find the primes. You can almost like find the primes in this sequence or whatever. You almost write that and it does it for you. So it's really cool to like read your program in English and it's just doing stuff. It's an ascendant language, I think, in the sense that like more and more companies are using it. So like Amgen, AT&T, Bank of America, Twitter, Google, Facebook, lots of companies use it. So, and I think one reason is because very good programmers like it, like Haskell. So these companies want good programmers. That's another reason for Haskell. And it just has, it's centered around category theory in some sense. It's a major inspiration for the language. And so these ideas we'll be talking about are really appropriate for it and help structure your code. And the type checker, for example, makes sure that you don't write completely stupid programs. They still might not do what you want, but somehow it's hard to write a bad program, hard to write a wrong program there. Another reason is that we're offering the course is we gave this class last year called 7 Sketches in Compositionality, where we gave 7 different applications of category theory. But we didn't talk about programming, and that's one of the biggest applications out there for real-world applications. Another reason, totally different, non-Haskell-related reason we're giving the class is just because we're bringing these communities together. So there's mathematicians and there's programmers, and maybe you're a Julia person. And that person is already bringing math and computer science together. But that's a little more. It's a beautiful language also, but it's maybe more on the optimization side. I'm looking at a Julia person right now. But we just have these 2 great communities, and there's people coming from all over, like internationally and throughout the country to come. So please meet other people while you're here and like hang out. Every day after class, we'll have a half an hour or maybe even hour-long period that you can just hang out and ask any question that you didn't get to ask during class and talk to people about whatever you want. It doesn't have to be math, but everyone here is kind of here for similar reasons. So it's great to meet people, and there's just a big community. And category theory is, I really like the community. So hopefully you will too. Finally, let's see. So there's this gap a little bit between category theory, which is a pure subject, and programming, which is an applied subject. And pure category theory is almost never useful in anything unless you at the very end let yourself break it. So it's like this Platonic ideal, like, if only Haskell was a Cartesian closed bi-category, bi-Cartesian closed category with list objects, then I would know what it was and it would be perfect and I could reason. But alas, it's not that thing. So what is it? And then you give yourself like this monad that kind of lets you escape. And so if you don't know what I'm talking about, that's fine. I'm using words for some people who do. And we will explain all these words. But basically, you have to kind of break. Math never quite applies. There really isn't like one goat or 2 goats. There's like a goat with like a mangled ear and a goat with like, nothing's perfect in this world. Nothing's perfectly math, and category theory is no exception. But there's this pure side for thinking and this applied side for doing, and somehow they almost relate, and they relate closely enough that one can be useful for the other. The thinking about the real world, even though it's all in this like thing made of meat inside your brain, inside your head, it is still somehow applying to this real world out there. And in the same way, category theory is still somehow applying to programming languages, and Haskell or its relatives are some of the best examples of that. So another reason for this class is to kind of clear the air around this, because there are some Haskell is not a perfect category. There are mistakes that people make. They say things like every endofunctor has both initial algebra and a final coalgebra, and you will know what that means by week 3. But that's not true. The identity endofunctor does not have that they coincide. There are just little mistakes people make, and we just want to have some category theorists here, have some programmers here, have a discussion, and make sure that we understand each other and we learn from each other. And so far, Brendan and I have learned a lot from Bartosz, and I think we've also contributed some ideas to Bartosz. And so that's what this class is all about, is really learning from each other and just kind of, yeah, learning from each other and learning from each other more. So to that end, what we're going to do, well, there's no prerequisites. You don't need to know what a set is or what a function is to take this class. But on the first day, this is the 0th day, on the first day, we will talk about categories by the end. So we'll start with like what is a set, and we'll end with what is a category. And so you don't need to know anything, but you do need to pay attention, to try to listen. And the best way to not lose attention is when you have a question, ask it. Because if you have a question, you don't understand something, and then you don't ask it, and someone goes on, then you're half paying attention to your question, and half, if you're me, and maybe you are me, I don't know, then you're half paying attention to your question, half paying attention to what they're saying, and you slowly drift into this other thing that's more important about like your social life or whatever thing I do, I don't know. So ask your question immediately, as soon as you can, as soon as you're comfortable to do it, and we really try to say, like, there are no dumb questions. The closest thing to a dumb question is if you think secretly that your question is going to make you look smart. And then you should check your motivation, because that's like, ooh, this question, while opposing it, sounds like I don't understand. The secret thing in my vehicle is that I actually understand like 3 levels ahead. That's not a dumb question, but it's not the question we're inviting. We're inviting questions where you don't understand something, or maybe there's a typo and you think someone else might not understand something. Like, please, hey, is that a typo? So we're like, come from contributing to the rest of the class and yourself and us. As like a teacher, if you ask a question and I notice, wow, that was unclear, that's like the most helpful thing. So I love that. So come from that kind of point of view, and I think it'll be a great class. So with that, I think I'll pass it over to Bartosz.
All right. So I'm really grateful to be here. Thank you for inviting me. And this morning I was thinking, you know, this is going to be a really strange course, because it won't be the usual thing. It's we have 2 mathematicians and 1 physicist teaching people programming. It sounds like a beginning of a joke, right? But it makes a lot of sense. I keep asking myself this question all the time, and they already asked this question also. It's like, why? Why is category theory suddenly become relevant to programmers? And I'm saying programmers. I prefer to say programmers rather than computer scientists. The computer scientists are sort of like mathematicians. They talk mathematics, but programmers are so down to earth. Programming is a down to earth thing. You know, people do this for a living. They actually get paid big bucks for programming, right? So it's a very practical thing. On the other hand, as Brendan said, this is category theory is this like very abstract part of mathematics. I would even say it's like maybe the most abstract, or like one of the highest abstractions in mathematics. So we have this really strange marriage between these 2 human activities, right? And until very recently, mathematicians really kind of ignored category theory. A lot of mathematicians didn't really get into category theory, and then suddenly there is this jump, quantum jump between applied category theory. Suddenly there are a lot of people interested in applying it to real life, bypassing sort of like all this hierarchy of mathematics. So in order to understand why programming and category theory are relevant to each other, you have to ask yourself the question, what is programming about? What's the essence of programming? And I've been a programmer for many years. I mean, I worked at Microsoft. So when I started programming, I learned assembly language. Assembly language, when you learn assembly language, you realize that it's an activity in which you are talking to a computer, and computer is like an alien. It says, like if you thought about a computer having a mind, it would be like a totally alien mind. It's very unlike others, like ours. It's it takes everything literally, right? It will execute whatever you tell it to execute. If you make a little mistake, it will just fail, right? It's unlike in human communication, like when we sort of hand wave and say things, right? And you understand what I mean. You know this kind of communication. With a computer, it's not. You have to say precisely what you want. And then the way computers deal with complexity is pretty amazing. It's like for a computer, there's no complex thing. It's just like whatever you throw at it, it will execute it. It can process, terabytes of data. There's no problem with it. It can run a program that has like it's full of go-tos and unstructured and whatever. From the point of view of the computer, there's no difference. So sometimes, programmers have this like inferiority complex. It's like, gosh, am I so stupid? It's like the computer is telling me you made a mistake here, right? It's like this is an error. This is on. It's like, and the computer can deal with all this data and all these go-tos, and I can't. So am I worse than a computer? Is my mind like weaker? On the other hand, a computer will never come up with problems, right? We are the ones who are saying, okay, we have this problem, we have to solve it. We translate it into a computer language. We tell the computer what to do, right? So we have a much different mind, as powerful or more powerful than the computer, but there is this impedance mismatch between us and the computer. And programmers have to constantly deal with this impedance mismatch, right? So when I was studying assembly language is very close to the machine. So it's essentially, it's almost as close as, flipping switches with zeros and ones. Like in the original computers, people were actually inputting programs by flipping switches, right? An assembly language is a little better. It has some crutches for humans so that we can deal with it. Like for a computer, a memory address, a pointer, it's just a number, a binary number. So here, store this data over there, move it from here to here, no problem, right? When we write a program, even in assembly language, we would say, okay, let's label this memory location with some meaningful name to us, right? The computer throws this name away. The assembler just throws it away. The compiler throws it away. The computer doesn't need it, but we do. So why do we need this? Because we humans, we have this small brain, right? We have a small capacity of dealing with complexity. So because of that, we have developed this strategy of solving problems. And this is so ingrained that we don't even think about it. But every time we have a problem, we always approach it by subdividing this problem into smaller problems, decomposing it, right? I mean, and next time you have a problem, think about this, how you are decomposing it, how you are splitting it into smaller sub-problems. And we do it recursively, right? These smaller sub-problems, we split them into even smaller sub-problems and so on, until we reach like this basic level at which we can say, okay, I know how to solve this. I have already solved this before. There is a library call that I can make, you know, or there is like a simple loop that I write and it will do the stuff that I want, right? So once we have decomposed the problem and got to the bottom of this, essentially a big tree, right? We start solving these little problems, and then we have to recompose the solutions. So this process of decomposing a problem and recomposing solutions is so basic in everything we do. But it's absolutely necessary and essential in programming. So when I worked at Microsoft, like one of my first assignments there was, I was a total rookie at programming, but they just threw me into this, and it's like, here's an operating system. You have to port this operating system. There was a group of people who knew much more than I did. We are porting this operating. This was a Mach operating system from CMU. Microsoft bought it, and there was a big plan to make the next version of Windows based on Mach. Didn't work out, but it was a great experience for me. So I had to like go into this operating system. I knew very little about operating systems back then. And the first thing you notice is that it's subdivided into components. So it had beautiful structure. It was written by real professionals. So there was like a subsystem that was dealing with processes, things that run in parallel. There was a subsystem that was dealing with virtual memory. This is the part that I was supposed to be working on. There was another part that was dealing with the file system, with networking, and so on. And the fact that I was assigned to work with virtual memory subsystem meant that I had to learn a bunch of stuff about this virtual memory subsystem, but I had to know a little bit about the other subsystems because they interacted with the memory subsystem, right? But I didn't have to know all the details about these other subsystems. And that's the basic idea, you know. Why are we splitting these problems into components? So that we can focus on one component and have limited knowledge of other components. And within this virtual memory subsystem, there were smaller subsystems. There was like a page fault handler. There were page tables, data structures, and so on. Each of them usually was located in some subdirectory in the file system. And there were source files, header files. Each source file, in turn, was contained like subroutines and data type definitions. And then the functions had lines of code, loops, and so on. So it was structured all the way down. All the way down, you could see little pieces that had small pieces that had even smaller pieces, and so on. Okay, so everything in programming is organized like this. And you have to be master of this. If you want to be a good programmer, you have to master this decomposition and recomposition idea, right? So how do we do this? So the question is, how do you know? Like when you are studying programming, okay, they tell you this is the syntax of the language, this is how an operating system works, and so on. But then you get a problem and you have to decompose it. You have to write a program. Like, how do you approach this? Nobody teaches you how to approach problem solving. Either because this is assumed that everybody knows how to do it, that there is some kind of evolutionary advantage to problem solving. And there's a lot of truth in this. Like we have built-in mechanisms in our brain for decomposing things and quickly solving them. Our survival depended on it. Maybe nowadays our salaries depended on it. But back then it was like survival, right? Like you see a dangerous situation, you have to quickly analyze it. You have to split it in subcomponents. Here's a tiger. Here are my teammates, who have arrows and so on. What do I do? Quickly, right? So your life depends on it. So during the evolution, and every animal has some mechanism of decomposing dangerous situation into subcomponents so it can deal with it, right? So we have this built in. Plus, when you are a programmer, you learn a lot on the job. So you see how other people decompose things. You see certain things. You study an operating system and you figure out, aha, so this is how they do this, right? So you gain experience. So evolution plus experience lets us do this, right? But there hasn't been any methodology. People would try to come up with methodologies for problem solving, and they would address like a small subset of it. So one of the things that we always do when decomposing things is finding patterns, right? So we are very good at finding patterns. Humans are extremely good at finding patterns. We can find patterns in anything. We can find patterns in random data, right? I mean, you look at the night sky, and you see these stars, and so this is not like Greek gods there, or heroes, or kitchen utensils in the sky, right? Nobody put them there for this purpose. These are random dots, right? But we see shapes, right? We see patterns there. And this is extremely useful because if you can recognize the Big Dipper, right, then you know where the North Star is, and it can save your life, right, when you are at sea. So this pattern recognition is a basic way we operate. And of course, programmers figured that out too. And they started writing books about patterns in programming. There is like a famous book, The Gang of Four Patterns in Programming. They just list a lot of patterns. And this is a typical engineering approach. Is you see a pattern, you describe it. And then other person will read this book, and when they see this pattern, they know that there is a solution to this pattern. But it is sort of at random scanning the area of programming and looking for patterns and saying, here's a pattern, here's a pattern, let's just write it down, right? But there was no general purpose pattern finding algorithm. There isn't one, right? So until recently, maybe the 20th century, there was not really a science of patterns, and then people came up with category theory. So category theory is this like a meta thing that actually talks about structure of things. And when it started, it was the structure of mathematics. It was invented by mathematicians to deal with mathematics. And they noticed that like there are all these different areas of mathematics, but there are certain patterns that keep repeating, you know. And they started studying these patterns, and eventually, you know, they found out that there's a lot of similarities, and they started writing books about it. Like MacLean wrote this category theory for working mathematician, you know, which is I started reading this book, and it was like first few lines took me a month to understand. Why? So this is why category theory was considered so difficult, even for mathematicians, because the first examples there were taken. You know, here's an example from algebraic topology. Here's an example from analysis. Here's an example from group theory. You know, now you see, right? You see the pattern. It's like, no, I don't see this pattern. So I started working on this, and I had to come up with my own examples. Okay, so I started searching, you know, Haskell libraries, and Edward Kmet was the guy who actually like introduced a lot of category theory into Haskell libraries. So I studied what he wrote and started figuring out. So it turns out that a lot of these patterns from category theory can be illustrated. Either can be translated into Haskell or can be illustrated by programming concepts. So if you want to like have a royal road towards category theory and you're a programmer, you have an easy way, because you know you can just forget about topology, forget about algebra, forget about all these things that you don't want to learn. Here are examples from programming, and they make perfect sense. So category theory like unifies all these things, and because of that, it's extremely useful when you want to like lift yourself above the like everyday programming chores. Like when you want to go outside of it, because all these patterns that we are using in programming have already been described. We know how to use them, and we use them and reuse them day after day, right? Where do we search for new patterns? Like if we want to tackle bigger and bigger problems, then we will need to find better ways of decomposing problems, right? So we have to be searching for ways of decomposing and recomposing solutions, decomposing problems, recomposing solutions. And category theory is just like this wonderful reservoir of ideas about composing and decomposing things. And there is some, you know, difficulty for programmers dealing with some abstractions, because you know they are familiar with certain patterns, and here there are new patterns that look nothing like nothing else that they've seen before. Like a lot of people have problems understanding what a monad is, right? That's like one example of things that I had to explain many times. And it's a very abstract thing, but it gives you a tool that's completely new tool for decomposing things. I mean, a monad is just about composition. It's like once you explain this, then it's aha, I've been doing stuff like this all the time, but I've been always doing it from scratch, not realize, and I was missing certain parts that like make it so obvious, right? So I think this will be a very productive thing for us, hopefully, that we learn both elements of category theory and programming in parallel, and they will feed on each other, and we'll be able to like break this barrier towards category theory, between category theory and programming. Thank you.
Do you want a moment to digest and I'll talk about? You can spare 2 minutes. Okay. Why don't, while we change over, turn to another neighbor, introduce yourselves, and just reflect for 2 minutes on what Bartosz just said. Maybe if you've done some programming, talk about your experience in programming, if you're comfortable, and whether you need more strong...
How many programmers do we have here?
Wow.
Okay.
How about people that are coming from a more mathematical background? Is
so great. You can raise your hand twice.
Yeah, you can raise your hand twice. Okay. Yeah, please introduce yourselves. At 2:45, I'll start sort of talking about just a quick overview of what we'll actually cover in detail and just course structure things. So 2 minutes. Great. Does anyone have anything that came up in the discussions that they want to share with the group? It's okay if not. It's a big group. Okay. So let's talk a bit, just sort of say a few technical terms about things that you can expect to show up. So for me, this course is about how to think using category theory. And as you've heard from both David and Bartosz, category theory is this sort of formal mathematics, formal science of composition, of relationships, of connection, synthesis, how sort of wholes relate to parts. So we're teaching tools so you can think about these subjects. The relationship to programming, at least for me in this course, is that programming is the vehicle to test whether these ideas are helping you to think in a practical way. The best thought has practical consequences. And so along the way, we'll teach sort of an abstract mathematical concept with precise definitions, but we'll also introduce Haskell, the syntax, how to program in it, and give exercises. And so you can sort of use, as you sort of learn these structures and learn this new way of thinking, you can see whether you can sort of do these exercises and write code that to begin with, type checks, compiles, but also performs practical tasks like, say, constructing a solitaire game or something like that, and maybe even more practical than that. Nothing's more practical than that. Bartosz has been working on that exercise for the last couple of weeks. I'm really excited. Anyway, okay, so what are the actual things we're going to cover? To begin, it'll be roughly split into sort of five sections. So the first is on the basic sort of fundamental tools, the fundamental definitions of category theory, and they come in sort of 3 parts. There's categories themselves, there's functors, which are certain sorts of relationships between categories, and the natural transformations, which are relationships between functors, because category theorists really like relating things. So what is a category? The basic idea is that a category studies errors. But it studies, as we've been talking about, composable errors. So you not only have these, you have these primitives, but given 2 of these things, you can get a third, get one that says sort of do this. This one is do that, then do that. And so how is Haskell sort of, how does this help us think about programming? How is something like Haskell modeling this? Well, you should think of this in this sort of fundamental analogy of this course as your sort of program, or maybe your, let's say it's a Haskell function. And what do functions do? They take an input and they turn it into an output. But it's useful to have a bit more structure. We don't want, if we have a function that sort of squares a number, we don't want to be able to sort of throw a string at it, throw like the phrase hello, and see what it does with it. So in Haskell is a strongly typed language. So this restricts what we're allowed to put in. So we have these things called types, like the type of integers or the type of strings, the type of booleans. And this is how we understand Haskell as sort of modeling this idea of a category. OK, so types are very important. And so notions like functors are realized in Haskell as type constructors. And then natural transformations, we'll see this in a lot more detail, but are sort of types, these things called polymorphic types, or very closely related to polymorphic types, which are polymorphic functions, which are sort of, you get a function for every type. Well, we'll get into that. So I guess on the Haskell side, on the other side of this, we have sort of types and functions, programs. What am I doing for time? OK, so types are very important. And the next part of the course is really about sort of constructing the types that you need to sort of effectively sort of lay out the structure of a program. So two concepts from, or one particular idea from category theory is very useful for this. And this is the notion of a universal construction. So category theory is about relationships. So a category has a bunch of these arrows, and they're all sort of doing things. But in certain categories, there are special sort of objects that can be determined. Like, for example, the type unit in Haskell has this property that there's a unique function to it from every other type. And so that from every other, this universal idea pulls out that type as a special object. And so we can characterize new types by just defining what relationship they should have to other types. So universal constructions, like products, you might have heard of, product types or sum types, are very much, so there's this relationship, universal constructions and algebraic data types. And the next, we'll talk about what are perhaps poorly named, but they're called sort of algebras and co-algebras for a functor. And these have a strong relationship to another sort of way of constructing types called a recursive data type, like recursive data types. So an example, I guess, is list. And then the fourth topic, after we've given some methods for constructing types, functional programming is a lot about sort of pure functions, but sometimes our functions sort of want to have consequences outside. So you might want to sort of write a log or wait for an input or something like that. And so even though functional programming is a nice clean paradigm to program in, for practical tasks, we need to sort of break this abstraction and talk about side effects. And category theory provides a nice tool for thinking about these called monads. So that comes next. And then finally, not so much a topic, but a promise of a topic, is just sort of special topics. So at that stage of the course, we'll have a sense of what people are interested in, and we'll sort of teach something that's exciting to us all. Maybe things like sort of optics and lenses and perfunctors or applicatives or something like that, but it's to be determined. It'll happen in the last week. OK, so that's an outline of what we're going to teach. This course is also an actual sort of MIT course. We're at MIT. And it can be taken for credit. Actually, before I get there, maybe I should just say this is relevant to everyone. When is this course happening? It's happening every weekday from now until the end of the month. This is every weekday. R stands for Thursday, except the 20th, which is Monday, MLK Day. That's a holiday. There'll be a class like this from 2 to 3 p.m. every day. And then from 3 to 3:34, there's sort of office hours. We think of it more as sort of just fun communication time. So we'll be sticking around here to ask questions, and hopefully you all join us and be excited about this stuff too. In terms of taking it for credit, if you're an MIT student, you can register wherever you register for courses. It's a pass-fail course. Register for 3 units, please. You're not going to get more than that because they won't let us give you more.
If you don't do 3 units, email us, and then we'll email you that you have to change it. So just do 3 minutes from the beginning, so we don't have to do that. Sorry.
And the grading is particularly simple. There's 25% for participation, which means just show up, ask questions, have fun. one way you can participate, and I invite you all to do this. This is the first homework. Just come up after this class or the next class and introduce yourselves to one of us. Tell us your name and why you're here. We'd love to get to know you. The next part, there'll be 3 P-sets that will be put out. They're sort of, in terms of grading purposes, they'll be worth a quarter of the grade each. And they're due sort of next Thursday, the Thursday after, and the last Friday, of course. So I think that's it. Any closing words from either of you?
Come afterwards and introduce yourself.
Yeah, and also one thing it would be really useful for everyone to have taking this course is just Haskell running on their computer. So there's some instructions on the website about that. If you have any trouble, now's a great time, or tomorrow after class is a great time to come up and we can help with installations. Bartosz, being the programmer among us, is probably best, but we can all try. Questions there?
How quickly do you expect to post the videos?
How quickly do we expect to post the videos? Hopefully the evening after each, within the next, I don't know, by like midnight after the lecture, but we'll see how it goes. And there'll be course notes too online. Anyway, okay, thanks everyone.